Apparatus for measuring the thermal conductivity of a gas. A long cylindrical wire of radius A and electrical resistance R per unit length. Radius A, it has electrical resistance R per unit length, is stretched along the axis of a long cylindrical container of radius B. So this is the container with radius B. This container is maintained at a fixed temperature T0 and is filled with a gas having a thermal conductivity kappa. So this is at T0. It's filled with a gas that has thermal conductivity kappa. Calculate the temperature difference delta T between the wire and the container walls when a small constant electrical current I is passed through the wire. So we have a current flowing through the wire. So this will heat up the wire and therefore there will be a heat flowing outward. Showed us that a measurement of delta T provides a means for determining the thermal conductivity of the gas. Assume that a steady state condition has been reached so that the temperature at any point is independent of time. Suggestion: consider the condition which must be satisfied by any cylindrical shell of the gas contained between radius r and r plus dr. So this is between r and r plus dr. The electrical power generated per unit length is P, which is equal to I squared times the resistance per unit length R. Remember that it has an electrical resistance per unit length R. And this is equal to the heat dq dt, heat flowing per unit time, per unit length at steady state. So this is a constant power. So we can calculate the heat flux, funny Q. This is 1 over the perpendicular area, the total heat flowing through that area, that is dq dt per unit time. Since this is heat per length, we have to multiply it by the length dz. And what is the perpendicular area? It's going to be equal to 2 pi r multiplied by dz. So that will be the side surface of the cylindrical region. So this will be 2 pi r multiplied by dz. That will give us the side area. So this will be the perpendicular area for the heat flowing outwards. So heat is flowing in the radially outward direction, as you can see here. Outside temperature is T0. And this is 1 over 2 pi r dz. The surface area that this flux sees as it flows radially outward, multiplied by the heat dq dt per unit time, per unit length, so it has to be multiplied by dz. So these dz values will cancel. So we obtain the following situation: 1 over 2 pi r dq dt. This is the heat, that's dt here, time. This is the heat flowing per area per time, because this was already per length. So this is divided by 2 pi r gives me the heat flux. The heat flux is minus kappa times dt dr. That's the law of thermal conduction. And at steady state, this dq dt, the heat flowing per unit time, dq dt, is a constant, and it is equal to I square, current square, steady current square, multiplied by resistance per unit length. So if I consider this equation and I isolate dt, if I integrate between a and b dt, this is going to be equal to integral between a and b For dq dt, I substitute I square r. Here I have dr going here, dr over 2 pi r. So that's dr divided by 2 pi r minus 1 over kappa I square r is substituted for dq dt. This is I square r. So this is the temperature at point B minus temperature at radial distance A. That's equal to minus I square r divided by 2 pi kappa. Now I have the integral of dr over r, which is natural logarithm r equals b divided by r equals a. So this gives me I square r divided by 2 pi kappa natural logarithm a over b. If I operate the minus sign here, this goes as to the power minus 1. So if I take this equation and multiply it by minus 1, I will obtain temperature at A minus the temperature at B. So a measurement of delta T provides a means for determining the thermal conductivity. So this is the delta T measured between points A and B. This is going to give me I square R divided by 2 pi kappa natural logarithm. So since I have multiplied this equation by minus 1, this becomes natural logarithm b over a again. So you can see that the thermal conductivity kappa can be found as 2 pi times delta t divided by I square r multiplied by natural logarithm b over a. So natural logarithm b over a at the bottom. So kappa goes here. This is not correct. So kappa goes here. So we have I square r divided by 2 pi delta t multiplied by natural logarithm b over a, giving us the thermal conductivity. So it's I square r natural logarithm b over a divided by 2 pi delta t. So if we know delta t, if we measure delta t, we know the current flowing through, we know the resistance per unit length and the radii b and a, we can determine the thermal conductivity. Okay, so this is an apparatus for measuring the thermal conductivity of a gas. Where is this gas? It's filling the space in between the wire and the outer cylinder with radius b. The inner cylinder has radius a. This wire, conducting wire, carries a steady current I, and it creates a power I square R, where R is the resistance per unit length. That's the power that is created per unit length. It is dq dt, the heat, because this is power, dq dt per unit length at steady state. And the heat flux is the heat flowing radially outward. It's 1 over the perpendicular area, which is 2 pi r times, at a radial distance r, 2 pi r times dz. That would be the area it sees. dq dt, this is per unit length, so multiplied by the length gives me the heat. So this dq multiplied by dz gives me the heat flowing radially outward per area per time. That gives me the heat flux. So 1 over 2 pi r dz, dq dt dz, dz's will cancel, and this heat flux is minus kappa dt dr according to law of thermal conduction. And since at steady state dq dt is equal to I square r, I substitute that here, isolate dt and take dr to the left hand side, dr over 2 pi r minus 1 over kappa I square r, integral from a to b dt. This gives me temperature at B minus the temperature at A, and this gives me the integral of dr over r, which is natural logarithm B over A. So TA minus TB is, without this minus sign, delta t I square r or 2 pi kappa natural logarithm B over A. So you can see that thermal conductivity is I square r natural log B over A divided by delta t. So with a knowledge of a measurement of delta t, we can determine kappa.